Welcome back to week 7 of the ma135 ma160 calculus. My name is Götz Pfeiffer and this video is about trigonometric substitution. We've already seen how an integral that arises in the determination of the area of a circle involves an integrand that is the square root of a difference of two squares. The root of a squared minus x squared dx. Here the usual substitution u for a squared minus x squared doesn't help. But somehow miraculously substituting a times sine theta for x does work, because you can go through this calculation where the difference of the two squares, a squared minus x squared, becomes a squared times cosine theta squared, from which one can extract the square root. And so now after the substitution, the square root of a squared minus x squared is a times the cosine of theta, or a times the absolute value of the cosine of theta. This is a substitution where x, the old variable, is expressed in terms of a new variable. And this is a different procedure from taking a part of the integral here, for example a squared minus x squared, an expression that involves x, and introducing a new variable to replace this part of the integral, introducing a new variable u in terms of x. This is in fact inverse substitution, where one substitutes for x a function g of t in terms of a new variable t. And in that case the substitution rule is used in reverse, where replacing the integral over f of x dx by the integral over f of g of t times the derivative g prime of t with respect to t. And despite the looks here, despite the fact that we're replacing a simple integral by a complicated expression, the idea of course is to simplify the integral as it happens in the examples, in the applications. This is called inverse substitution, applying the substitution rule backwards. In the original substitution we were trying to construct an expression of this form, f of g of t times g prime of t dt, and then replace this as our original integral by the simpler integral over f of x dx, or f of u du, where the u then is the new variable. Here we're going the other way. We're replacing the integral over f of x dx by the integral over f of g of t times g prime of t dt in a process called inverse substitution. Let's see this in action. So here's an example. Here's the integral over the square root of 9 minus x squared divided by x squared dx. Similar to what we've just seen, here we're looking at the difference of 9 and x squared, the difference of two squares under the square root. So following what worked on the previous slide, we replace x by 3 sine theta. Let's take the value of theta between minus pi over 2 and pi over 2. Then dx is 3 cosine theta d theta, differentiating x with respect to theta here gives dx as 3 cosine theta d theta. And as before, the square root of the difference of the two squares becomes 3 times the cosine of theta, 3 times the absolute value of the cosine of theta. But here, if we're choosing theta between minus pi over 2 and pi over 2, the cosine will always be positive. Cosine of theta over this range is positive. So this is just 3 cosine theta. That's the that's following the earlier example. Now we're looking at the square root of 3 squared minus x squared, setting x to 3 sine theta. This is expressing x in terms of a new variable theta. The dx becomes the derivative of x with respect to theta. That's 3 cosine theta d theta. And the difference of two squares becomes a square of which we can extract the square root to be 3 cosine theta. So that's the inverse substitution set up in this example. And the given integral now becomes the integral over 3 cosine theta at the top, and at the bottom, x squared. If x is 3 sine theta, then x squared is 3 squared times the square of sine theta, right? So that's 9 sine squared theta. All of this followed by dx, which now is 3 cosine theta d theta. And there, okay, these scalars, the multiples 3, 3 and 9, they all cancel. Then we're left with 2 factors cosine theta at the top and 2 factors cosine theta at the bottom. That's cosine squared theta divided by sine squared theta. And that is, of course, the square of the cotan of theta. And this square using a variant of the basic trigonometric identity that we saw recently. This square can be expressed as the square of cosec theta minus 1, and the square of the cosec theta can be integrated to minus cotan theta. That's a trigonometric integral that we found on the tables not too long ago. The integral over the square of cosec theta is minus cotan theta. So this integral then becomes minus cotan theta minus theta plus c, the constant of integration. And we need to back substitute. Now, this is going to be a bit of a challenge, because the substitution we've been using was expressing x in terms of a new variable. Now we're left here with a formula in the new variable, and we're faced with the task of expressing the new variable back in x. Now that requires a bit of work. Okay, we can divide this by 3 and then take the inverse sine function to express theta itself as 1/3 of the inverse sine of x. That deals with the theta. For the cotan of theta, we might unwrap the definition to try and get 3 sine thetas in there somewhere. we're somehow working this backwards. The cotan of theta, of course, is cosine theta divided by the sine theta. Since here we want 3 sine theta, we'll divide 3 cosine theta by 3 sine theta. And then working this trigonometric trick here backwards, we can express cosine theta in terms of sine theta, or rather 3 cosine theta in terms of 3 sine theta, by writing this as the square root of 9 minus 9 sine squared theta. And now replacing 3 sine thetas by x, this becomes the square root of 9 minus x squared over x squared. For the cotan theta expressed in terms of x is the square root of 9 minus x squared divided by x squared. Oh, that's the old integrand. Anyway, that now solves the integral. Back substituting the substitution gives the integral as minus square root 9 minus x squared divided by x squared minus the inverse sine of x over 3 plus a constant of integration. Of course, that's what it should have been all the time. There, the theta is the inverse sine of x over 3. Dividing this equation here by 3 and then applying the inverse sine gives theta as inverse sine of x over 3. That's expressing the cotan of theta in terms of x by working through various trigonometric identities. Alternatively, one might do this in the geometric setup with the triangle, where in order to express the cotan of theta in terms of x in the given under the current circumstances, where we know that sine theta is 1/3 of x. Now we use the diagram. It helps to draw this diagram of a right-angled triangle. There's the right angle, which has the theta there as one of its angles, and since sine theta is opposite divided by hypotenuse, and sine theta is x over 3, we can label the opposite side as having length x, and we label the hypotenuse as having length 3. And then by Pythagoras, we know that the squares of the x and the so far unlabeled side must add up to the square of 3, which is 9, and therefore the unlabeled side must be the difference of the square of 3 and the square of x, and then the square root of that. So that's Pythagoras, which gives the side length of the third side of the adjacent as square root of 9 minus x squared. And from that we get the cosine of theta, or rather what we're interested in is the cotan of theta as adjacent divided by opposite as square root of 9 minus x squared divided by x. That's the same formula for the cotan x, this time derived in a geometric fashion. Here's, as an overview, a table of situations where trigonometric substitution in one form or another applies. There's 3 situations that can be distinguished where because of the trigonometric identities, things work out well. So there's the case that we've been working with, where the integrand involves a square root of a squared minus x squared. In that case, the substitution x equal to a times sine theta works, because then the identity 1 minus sine squared x is cosine squared x can be applied to turn this difference of squares into a square of which one can then extract a square root, as we saw in the example. Variations of this then deal with the square root of a sum of two squares, a squared plus x squared, where the substitution x equals a times tan theta works, because of the identity 1 plus tan squared x is sec squared x, and that then turns the sum under the square root into a square of which one can extract the square root. And the last case on the list here is the difference of squares the other way around, x squared minus a squared. Here, using the substitution x equals a times sec theta works, because of the identity sec squared x minus 1 equals tan squared x, which is the same as the one above, but applied in a different context here. I should say that in each of these cases theta should be restricted to a suitable interval in such a way that the substitution function is 1-to-1 and can be inverted for the purpose of the back substitution. But that's more like a technical issue. Let's look at another example. Let's try and find the integral over 1 over x squared times the square root of x squared plus 4 dx. So here we're looking at an integral that involves a square root of a sum of squares, and according to the table, square root of the sum of the square of a and the square of x is a case for the substitution x equals a times tan theta, where a is the number whose square occurs here under the square root. So in the example, the x squared plus 4 is the square of 2. So the table suggests the substitution x equals 2 tan theta. Then by differentiating x with respect to theta, we get that dx, the differential dx, is 2 times sec squared of theta d theta, and our inverse substitution now gives the original integral as dx is replaced by 2 sec squared theta d theta, and at the bottom we get x squared. That's, well, if x is 2 tan theta, that's 4 times the square of tan theta, and under the square root we get what? So x, and we get x is 2 tan theta, so this becomes 4 times the square of tan theta plus 4, where we can take out the 4 as a common factor and actually extract the square root. So this becomes 2, cancels with the 2 upstairs, and this factor 4 we take outside as 1/4. And then tan squared theta plus 1 is one of the identities. Tan squared theta plus 1 is sec squared theta. So the square root of sec squared theta is sec theta, and then the integral becomes the integral one quarter of the integral over sec squared theta d theta divided by tan squared theta times sec theta, where of course one copy of sec theta cancels both top and bottom, and then we're left with a quarter of sec theta over tan squared theta d theta. Now recalling that sec theta is 1 over cosine theta, and tan theta is sine theta divided by cosine theta. There's again one factor cosine cancelling, and we're left with a quarter of cosine theta divided by sine squared theta d theta. And that that's a nice integral where we can substitute u for sine theta, and then the cosine, then du is cosine theta d theta, and the integral over 1 over u squared is minus 1 over u, so we get minus 1 over 4 sine theta back substituting plus c. So I did the u substitution mentally rather than write it all out. This is substituting u for sine theta here, and it all falls into place. And back substituting gives then minus 1 over 4 sine theta plus c. And you see how we've used this version of the trigonometric identity. Tan squared theta plus 1 was replaced by sec squared theta, and then the square root was extracted, and briefly at the end the substitution u for sine theta. But we're not done yet. We still need to back substitute the theta here in terms of x, which again is a bit of a challenge, but using a triangle as before, a right angled triangle with one further angle theta, then what we know is that tan theta is x over 2. So this allows us to label the opposite side with x and the adjacent side with 2. Pythagoras then makes the third side the hypotenuse, the square root of the sum of the squares of the other side lengths. That's the square root of 4 plus x squared. And therefore the sine of theta as opposite divided by hypotenuse becomes x over the square root of 4 plus x squared. And that's something we can substitute in the current form of the integral, and finally arrive at the value minus square root of 4 plus x squared divided by 4x plus c for the integral. And then I think this example shows how what looks like a process that makes things more complicated, this inverse substitution, expressing x in terms of a further variable theta, doesn't in fact make things more complicated. At the end of the day, lots of things cancel out. We're left with we're left with an integral that we can actually solve, as opposed to the starting point where simple substitution wouldn't get us anywhere. Finally, as a sort of a practical example, let's come back to the area of a circle, or more generally, the area enclosed by an ellipse described by the formula x squared over a squared plus y squared over b squared is 1. That's in the xy plane, the set of all points, that set all points x with x coordinate x and y coordinate y, that satisfy these equations. This equation for given values of a and b. If you think about it or try out a few things, you'll see that on the x-axis, minus a and a are points on that ellipse, and on the y-axis, minus b and b are points on that ellipse, and then the ellipse is the ellipse between these points. Let's try and use integration to determine the area of the inside of this shape. So in order to do this, we need to somehow express this shape in terms of a function that we then can integrate over. So first step is to take this equation and solve it for y, so y squared first. I'm multiplying both sides with b squared, and then taking the a squared to the other side and extracting a square root. Then we get y is equal to plus or minus b over a times the square root of a squared minus x squared. And since this shape is symmetrical, and what's above the x-axis here is the same as what's below the x-axis, and what's to the left of the y-axis is the same as what's to the right of the y-axis. In fact, the area in question can be described as 4 times the bit between the x-axis, the y-axis, and the part of the curve here in the first quadrant. In terms of functions, in terms of integrals, we can say that a quarter of the area in question is the integral from 0 to a here on the x-axis over the positive part of this equation between expressing y in terms of x. So that's the integral from 0 to a over b over a times the square root of a squared minus x squared dx. Here again we substitute x equals a times sine theta. Finding the derivative of x in terms of theta gives dx as a times cosine theta d theta. Here we're looking at a definite integral, so for the substitution we need to substitute the limits here of integration as well. So when x is 0, then sine theta, where a times sine theta is 0, and this for theta this means that theta is 0. 0 is the theta where the sine theta becomes 0. And also if x is a, then if a times sine theta is a, then sine theta is 1, and theta is pi over 2. Pi over 2 is the value for theta, which makes sine theta equal to 1. With the substitution we have in mind, a squared minus x squared becomes the a squared times cosine squared x, of which the square root, of course, is a times cosine x. So the integral becomes, the area becomes 4 times b over a taken out as a factor the integral from 0 to a over the square root of a squared minus x squared dx. Now with the substitution becomes 4 times b over a, the integral from 0 to pi over 2, times the a times cosine x from here, times dx, which is another a times cosine cosine theta d theta. So this is then taking the two a's as the factors outside is 4ab times the integral from 0 to pi over 2 over the square of cosine theta d theta, and that's the case for the half angle formula, where we replace cosine squared theta by half of 1 plus the cosine of 2 theta d theta, the half angle formula, and that is now straightforward to integrate. And an antiderivative here is, okay, we cancel the half against factor 2 in the 4, so this is 2ab times the expression 1 plus half of sine 2 theta evaluated between pi over 2 and 0, and since the sine of 2 theta is 0 at these two endpoints, sorry, that sine, what this is theta, this is, sorry, theta, this is here, so this is, the sine of 2 theta is 0 at the two endpoints, so this is just theta evaluated at pi over 2 and 0, and so this comes out as pi times a times b. A nice formula for the area of an ellipse described in terms of these parameters a and b. In particular, if a is equal to b, and then we're talking about a circle of radius r, say, and the formula gives us the area of the circle with radius r as pi times r squared. No surprise here, so the message is that these well-known formulas can be derived by integration and trigonometric substitution. So we've seen that substitution is important. The normal substitution we've been using all the time here. We've seen that trigonometric integrals involve certain combinations of trigonometric functions and how they can be solved with the help of trigonometric identities. Notably, the Pythagorean identity sine squared plus cosine squared of x is 1, and the half angle formulas we've used. Trigonometric substitution we've just looked at is a kind of inverse substitution, where the substitution rule is used in reverse, and it applies in particular in 3 situations where the integral involves radical expressions of the form root of a difference of 2 squares or a sum of 2 squares. That's it for now.